And it said recording will start when screen sharing starts. So
Okay.
I guess I should do that. Screen sharing. Are you able to? I think so. I don't know what I'm going to be sharing yet. Okay, can I say, oh no, I guess I have to say do it. Okay. It'll work. Hey everybody, so now I've gone into a presentation mode with a PowerPoint, so I can't actually see you anymore. I can't make eye contact, and I can't even see myself. So hopefully this will work, and let me know if you're not seeing what I'm talking about. The screen share has a slide up that says, put on your cosmic visors. And this is an activity that we've adapted to be an activity that maybe you would lead as a group leader at one of your meetings with your kids. Okay, when it says put on your cosmic visor, you will be getting some theatrical gel. It comes in long rolls. It'll probably be cut into sheets that then you will cut into smaller pieces, and you're going to have to make a visor kind of like this. We just cut up manila file folders and cut an opening in it, taped the theatrical gel in here, and then took the extra part of the folder and made these strips, taped it all together, and then you put it on, oops, like this, and we'll paper clip it in the back. Okay, so that's the idea. Because we haven't gotten you the stuff to make your own visors, to do this activity, I've created a little filter set that I'm going to slide across my webcam. So when it says put on your cosmic visors, that's what it would look like when the kids put on their cosmic visors. Okay, so in this activity, and you want to make sure everybody has their visors up, and there are 3 different colors. So you'll give some of the participants a blue visor. Some of them will have a green visor, and some of them will have a red visor. So the idea is that you're going to step through this PowerPoint with them, asking for comments about what they're seeing. So the setup is that you are the commander. They are aliens from another world, and they have alien eyes. And what do you notice about your vision? I'll ask the red aliens. What do you notice about your vision?
Oh, it's not as bright.
Okay. It's gotten dimmer. Is there anything else unusual about it?
You lose some detail.
Yeah.
What kind of detail do you lose?
Well, initially I could see more clearly details on your face, for example, and I'm losing part of that detail on your face. I can still see the same shape and outline, but some of the details of, I don't know, skin texture, whatever, they're not the same. You don't have as many light and shadow on your face.
Okay.
There is a glare on your map or whatever is behind you, or unless that's just the coloration, but there's a certain yellow that's standing out.
Oh, okay. And how about green aliens? What do you see? How do you see differently?
Brighter.
Right.
Okay. Anything else different about it? I kind of, perhaps I gave some of it away by calling you green aliens.
Everything looks green.
How about this set?
Some things are dimmer than were in the green one. So some things stand out in red, and other things are standing out in blue, and they both stand out in the yellow a little bit in the images behind you.
So you're getting that perspective because now you've looked through all three. Your kids will each have just one color. You'll divide up the group into a red set, a green set, and a blue set. So let's proceed now, and in a little while we'll do a comparison that you got to do by looking through these three different ones. Your job, so now I'm talking to you as if you are the bunch of kids with the visors on, with these things on. Your job is going to be to report back to me, the commander, as you visit planet RGB. You have arrived, and we're going to have you look through the window and report back. So, first set of aliens, here is what you see through the window.
Hold it up a little bit higher, Susie. Yeah, there you go.
What do you see?
All I see is a dark rectangle.
Yeah. Anybody else see much?
Is there something in the bottom right? Bottom. It might be your left, Susie, dependent. Yes, that section.
Oh, okay. You think you see something down there? Is that Christy?
Yes, that was me, and it moves when the frame moves, so it's not likely to be reflection.
Okay. Okay, let's ask the next group of aliens. What do you guys see?
Wow.
You can go a little bit closer, Susie. That's good, right there.
Now there's definitely a tree and landscape.
Ah. Okay, so you think you see a tree and a landscape. And what about you guys? What do you see?
Black.
Red aliens.
Circle in the corner, right corner.
Ah, you see something up here?
Mm-hmm.
Okay. So with each one of you is seeing different information, and if we can combine all the information, we might get a more complete picture of what planet RGB looks like. You said there's something bright up here in the sky. One of you said there was something down in the bottom here, and then the green aliens described quite a busy landscape without calling out these other two details that the red aliens and the blue aliens could fill in. So each one of you contributed a different piece of the picture to give us a more complete view of the planet. Now we're actually receiving a message from planet RGB. Do you think you can decode it? Let me hold this up the right way. Here's the message that we've received. What message are you getting?
4, 3, 2, 1.
How about you guys?
A little lower, Susie.
H-E-I-F.
Help.
Help!
Help.
And you guys?
Oh, can you?
Hi. Hi.
There you go.
Hi. Okay, so now we've gotten 3 different messages, and if we put them together, it's kind of important. One is actually a rather friendly message, and then the countdown and a request for help. So depending on how you're looking out at this world, you're going to see different things, and you're getting different messages depending on how your eyes are working. And what I'd like to do at this point is take off the filters and show you the 2 images that you are working with. So this is the landscape looking out the window.
Susie, is it possible to show that on the PowerPoint also for the recording?
Yeah,
Okay.
I will at the end. At the very end, I'll go ahead and show this. And then this was the secret message. So you can see how this one actually, with very little overlap, makes sense in white light. This one doesn't make so much sense in white light. And by using the filters, you can tease out the three very different messages that are a part of this image. And that makes a connection more to astronomers, because they're using the filters as well. And really for that same reason, to tease out different bits of information. They allow some wavelengths of color through, block others. So when you're looking with the green filter, red turns black, and all you see is the bright green. So you're blocking out some of the noise with filters as well. And this is how we discover more about some of these astronomical objects. So let's take a look at one here. This is an example of an object that's seen through three different filters, and you can see that we've labeled them. There's the red image, the green image, and the image taken with a blue filter. And it's funny calling it a red, green, and blue image because it still is a black and white image on the detector, okay? And this is the Dumbbell Nebula in the Summer Triangle up in Vulpecula. It's produced by a dying star. The shell, the outer shell of a dying star that's been ejected. It's possibly what our sun will end up looking like. And the red light here, by using the red filter, we're highlighting the light that comes from excited hydrogen. The blue and green comes from excited oxygen. So those two different filters, because of the specific wavelengths of light that they're letting through, tell us something about the composition of this object. We also sometimes use color to represent aspects of an object that would otherwise be invisible. So let's take a look. By using, say, a radio telescope or an infrared detector or X-rays, using some of those wavelengths that our eyes are not sensitive to, we can get an image of what is out there because some of those objects are emitting in those wavelengths that we're not normally sensitive to. So by using a different kind of detector, we can represent that invisible light with color. And that's what we've done here with the Omega Nebula. So this is a radio image up at the top, and we've colored that red. This is using an infrared filter, and we colorized that green. And this is just a visible light. We represented that with blue. So this is, you might be tempted to call it false color. We prefer to use the words representational color because it's representing what would otherwise be invisible. And I'm going to click through these kind of quickly just to keep us on track here. This is the Omega Nebula, M17. And here, again, we're representing the invisible, the infrared, with red. Red is visible, but we're representing it with green so that it contrasts with the infrared, and then the green is represented with blue. So that's completely wacky. It's not at all what you would see with your eye if you were out in space trying to observe this thing. But it helps us separate out those three very different images of the Omega. And this is another planetary nebula, which is the result what our sun might end up looking like at the end of its life. It's blasted out those outer layers. The shell of gas is excited by the star that's left over at the center. And here, the different colors represent different gases, like the nitrogen, the hydrogen, and oxygen gases. This is a Hubble image. And here's a Crab Nebula. This one, we're representing again invisible, so like the X-rays. This is a more energetic star death. This is a supernova remnant. And the higher energy is represented by higher energy light. So we're looking at it with X-rays, and that's not something that you could see with your eyes. So using the Chandra X-ray Observatory, we've represented that emission here with light blue. The visible is green, and the dark blue is infrared. And I think this is the last astronomical image that I'm going to share here, M83. And again, we're looking at radio near ultraviolet and far ultraviolet. This is a detail you would be able to see except with these detectors. And so this is the landscape that we looked at earlier. And our particular printer, when I printed these off, you didn't really see the little berries over in the bush here very well on this particular picture. But if you're showing this as a PowerPoint with everybody using the visor, you should have a bright enough image that those kinds of details will stand out better. And just very quickly, there's the Hi Help 4321. And that's it. Are there any questions about this activity? My screen just did something a little bit crazy. Everything just turned blue on me. So I think I'm.
I don't
Pardon
see
me?
you anymore.
You don't see me anymore? I got a message that I have a slow connection and I was shutting down the webinar. So I said, okay, that I could stop sharing my camera, but you can still see. So if anyone has any questions, I'd be happy to address those.
How do you know what colors to represent, or do you just randomly pick what colors you're going to have represent the different items?
You know, that's a huge debate that went on when they started releasing these pictures, because there's decisions that you would make for scientific reasons to enhance contrast and really be able to tease out the different details, and there's other aesthetic decisions that you would make. And I think the Hubble team in particular has done a really masterful job of balancing the science with the aesthetics. And that's one reason the public has become so attached to the Hubble images. Very few of them are trying to represent what it would look like to your unaided eye. They're not trying to make it natural color. It's the vast majority are representational color, and there's a high degree of aesthetics in there.
There's a question from Mary. She asked, when do you introduce the different wavelengths to the kids? I don't know if they study that in middle school.
Ah, that's a good question. You could start with like a rainbow activity where you have a prism and break up the white light into the full spectrum. If they have not gotten the idea that white light is a mixture of all the different colors. That's a very important point, that you would want to start with that before you introduce the filters. Okay, well, I think I should change Catherine over to be the next presenter, because she's going to talk a little bit more about the scientific use of filters. I think this is a fun use of filters, but it does have a scientific application.
Was it Catherine or Sue Ann who was going to do the screen sharing?
Has Sue Ann joined us?
Yeah, I'm here. Can you guys hear me?
Yes.
Yep.
Okay. Actually, it was going to be Vivian.
Oh.
But if she's not on, I can't tell whether she's on or not.
I don't see her.
I don't see her.
Because nobody was here today to put the program on my computer, and Vivian said she on hers.
So Catherine, are you?
There, but I can do it. I've got it on my computer.
Let's try that.
Okay. So can you guys see my computer?
Yes.
Right now? Okay. Cool. So one thing I was going to start with is the actual activity. And some of the main questions from this Investigate Filters activity are what are filters, what do they do, and how do we use them for astronomy. So maybe you guys can just kind of put forth your ideas and your thoughts about the activity right now. So how about this? How about what do filters do? Or how does a colored filter affect an image? Let's do that one.
So chime in, you guys, and tell us what you thought about that.
So they should only allow a certain color of light to pass through the filter.
Okay, so kind of like the green alien saw everything that was in green.
Right.
Any other ideas?
We see one kind of filter is the UV protection in our car windows that we maybe don't realize is there. And so
okay.
it doesn't just apply to visible light.
Yeah, that's a really good point. And then Susie touched on another thing about why astronomers might want to use filters. Anybody want to summarize why they think astronomers might want to use filters?
They can fixate on different objects or aspects of those objects.
Yeah. Anything else?
Think about some of those color pictures where, so in particular in using filters, where we talked about the different kinds of gases that were glowing in
right.
those
So
colors.
if you use the right kind of filter, it might even tell you what something's made out of.
Exactly. Yeah. Yeah. So even though you're blocking a lot of the light when you use a filter, you're sort of zeroing in or honing in on a particular aspect that you might be interested in that might be drowned out when you just get all the light. Yeah, those are really good points. So I'm going to go ahead and open up. Oh, first of all, I want to point out this link here. Did everybody? I saw on the discussions that people were wondering what the wavelengths were for the different filters. So it is kind of hidden, and it should be in the resources, but there is buried in this activity a link to a PDF of the Skynet filter descriptions. I went ahead and downloaded it to my computer, and it's just a PDF file that looks like this. So you can see, can you guys see it on my computer?
No.
Yep.
Yes, okay. So so here we see that the Sloan Digital Sky Survey filters, we see that they're mostly, colors of the rainbow that our eyes would see, except for like the infrared. But it gives, well, and the ultraviolet, I guess. And it gives the central wavelength peak of what this filter is designed to focus in on. And here's a little rainbow chart here to show you, 700 nanometers is kind of red, and 550 is about green, and 400 is more of like the bluish purple side of things. And then we also have these other ones like H alpha and O3. These are the ones that Susie was talking about that focus on an actual element. So H-alpha really focuses on hydrogen, and the O3 filter really focuses on emission from oxygen atoms. And those show up in sort of red and green parts of the spectrum.
So it means really that you have such a narrow filter that only from those atoms will come through, not a focusing technique of the telescope.
Yeah, these other ones are more like a range, and that's why they say central wavelength. That's there's definitely a range around that central wavelength, but these narrowband filters are so narrow that it's basically, it's mostly just a very narrow window around this central wavelength here. And then we've got the astrophotography ones. These are good for replicating kind of close to where your eye could see. And then, of course, the open and maximum light ones that you've probably mostly been using before this activity. So I just wanted to point that out as a resource to you. I know it's not in the resources page right now. Hopefully it will be at some point. But again, that can be found right here in the filters activity under step 2. So any questions so far?
I have a question. This is Meg.
Hi.
How are the photography filters different from the Johnson-Cousins filters, like the blue, red? Like if I use red, how are the different reds? There's a small R, a big R, and one that says red.
That's a really good question. I think it's just a different red wavelength, and I don't know the Susie or Sue Ann or Anna. Do you guys speak to that?
The Johnson's Cousins filters, and we should also call them Krohn filters, because Rich Krohn's father was really part of this wave in astronomy to standardize the filters so that astronomers at different telescopes could say with confidence that they were replicating somebody else's experiment because they were letting exactly the same wavelength of light through. So astrophotography filters are just not that precise necessarily. I mean, if you go to an Orion telescope store and you say, I want to buy some filters for my telescope so I can make pretty red, green, blue pictures, you might buy these astrophotography filters. But the Johnson's Cousins Krohn filters are just very specific. They're very standard, and so you can, if you're reading the research and you see somebody else has used those same filters, you can be confident that you can replicate their results. So for Skynet Junior Scholars, for the kids, we're hoping that we can convince our programmer to make something that says, give me any filter that's reddish, just to optimize your chances of getting more than one telescope that could collect the data. You know, that we, for our purposes, in a lot of cases, we don't need to be that accurate. But then if you want to compare your picture, your image to something that was in the literature, you do want to use the same filter. So that's kind of a hand-wavy explanation. And the main thing is, I don't know exactly what the astrophotography filters pass, but you can look up Johnson's Cousins filters and find graphs that show you the wavelength range that they actually pass through.
Nice. Any other questions?
Tam's trying to talk.
Oh. Maybe Anna can see if she's typing something.
Can you use two filters to overlap to get a combination of light through, or to block all but that type of light?
That's a really good question. So you actually, each image only has, one filter on it. And so, yes, so you need a computer program to sort of combine them, or you can look at them side by side in Afterglow, and maybe you can pick out just by eye what you're maybe looking for. But to actually combine them, you need a software program, and the one we're using is called Astro Image Processor, and I'm going to talk about that in a little bit. But yeah, you can't. There's no mechanism on the telescopes to have like red and blue filters on the telescope at the same time, so that your image is the result of what comes through both of those. That's a really good question.
So let me also do a quick demonstration, because this is something that I would encourage you to have answered on your own if you had the filters in hand. If you are looking through a red filter, I've reactivated my webcam. Can you see me again?
I think I might have to share with you.
I can
change presenter.
No, I'm just putting it over my webcam so it's on my face.
Oh, never mind. Sorry.
Do you see my face in red again?
Yes.
And this is the blue filter. And what if I put the red filter over the blue filter? What do you see now?
Nothing.
Completely black.
And why is that? The blue filter's letting what through?
Just the blue.
And what does that mean that it's not letting through?
None of the red.
Exactly. So it's not letting, and the red filter is only letting red through. So is there any blue to get through the blue filter when you put both on top of each other?
No.
No.
Okay, so that's something, I'm sure your kids are going to try this because they are going to want to put the red and blue together and have a purple filter. But light filtering is different than light mixing.
That's a really good point.
Yeah, so that's definitely something, that was a great question, and it's something that your kids are all going to ask. And it's a real simple, put it back at them, say, well, what do you think? And have them try it because it's pretty dramatic. Okay, I'm quiet now.
Awesome. No, that was great. Thank you, Susie. So just for the sake of time, I think I'm going to go ahead and move into Afterglow and open up some images that were taken in different filters. And I'm going to open some of my own, which is in the SJS pilot group, which I don't know if everybody can see that, but that's okay. I'm sure you have your own images that you can use too. I took a picture of Eta Carina. It's a nebula in the southern hemisphere. And I did a bunch of different filters. I'm just going to go ahead and open them all up here. And Afterglow takes a little bit sometimes.
And while you're doing that, while we're waiting for that to load up, one last bit with the colored filters, I just wanted to add was that first PDF that you brought up showed that it's a color wheel. And with the telescopes, you can only use one filter at a time. It's a wheel that's rotating through. And so you would take one image with one color and then the next image with the different filter. So you physically cannot combine them in the telescope. Okay. I'll let your images keep loading there.
Yeah, it takes a while. There's one. So you guys can kind of see the V filter image, the nebula, and we get a little bit of this gas structure here, and this star in the middle is kind of overexposed. It's taking longer than I thought it would. Maybe because I'm video chatting on my computer too. Maybe that slows it down.
Yeah, that was happening with me. I actually got an error message that said you're slow, so turn off your webcam, and I did.
Yeah, and this is strange. It doesn't let me use my cursor in the window anymore.
Catherine, do you remember your exposure time?
I do not remember it. I could check if my mouse was working.
So Joanne is checking that
Okay.
exposure time for you.
Okay. Thinking I might need to just try again. Skynet / Afterglow.
Again, while we're waiting, somebody had posted a question about how you get to open up images in my group. And I posted an answer today, and that is that you have to use the file, the word file, to open up your images instead of the little folder that looks like a file folder. When you use the word file, you'll see my images and my group's images pop up.
This is Meg. I'm the one that posted that question. And so what I figured out was not only do you have to use the Word file up top, but you also have to use your little file folder up button so that you get all the way back to the top where you could only see open images or open DS image. And if you've been working with your own files, the group files disappear until you get up to that very top level. And so you have to sort of close everything down and then start over, and then the group images will pop up again. But if you've been working with your own images and just scroll up with the up file folder, it still won't pop up with the group images unless you're at the very top level. Does that make sense?
Yeah, so you might have to turn off Afterglow and open it all back up again straight from the web page or something.
Right, yeah.
So because it really, these are going to the programmer. So do not be shy about saying, hey, this is not working, because it really helps to have other into me. All right, so I have, I go to, are you having better luck now?
I just closed my web browser and I'm starting over. So I just won't try to open as many images. I'll just try to open one at a time right now.
Okay, so I just clicked on the one that you did with the U filter, and it said exposure length 50, so 50 seconds on that one.
Mm, 50 seconds. Yikes.
I'm going to turn off my webcam too. A little.
Yeah, maybe that would help if I turn off my webcam. Okay, so here's, so you guys saw the, what was it, U or V that I showed you before?
V.
V, okay, and now here's the O3 filter, and you can already tell it's different. That star in the middle is not overexposed this time. And then I'm definitely seeing more structure here on this cloud. So let's try opening one more. How about H alpha?
Oh, wow, that's way different. I'm looking at it on my own Afterglow. That's really amazingly different.
Yeah, they're all really different. I definitely recommend trying out these different filters on a nebula. Let's see here. So here's here's H alpha, and I think it does look even a little bit different than the oxygen filter. So that star is back to being overexposed, but I see a lot more structure in the gas and dust over on the left side of the image. And this area over here on the right is still a little bright, but it's not as drowned out as the other one. So I made a color picture with these. I used the Astro image processor program to do this. Oh, I have to log in again. Oh, my computer's so slow.
What happens on a snow day?
Yeah, I guess I should be thankful that I have internet right now on the snow day.
To be thankful you have power.
Yes. Did you lose power, Samantha?
No, at least not when I left this morning. So I'm the only person at work in the whole NRAO here in Green Bay.
Yeah, I'm surprised to see you there. Okay, so here I am in resources, and you see that there's here's download Astro image processor.jar, and so that'll just take you to a quick little place to download the program, and here it is on my desktop. And to learn how to use it, you can go to the explorations and do the bonus activity, of making a color image. And there is a nice video tutorial with step-by-step instructions where I made a color picture of the Ring Nebula. And I'll go ahead and show you what resulted when I made my color picture out of the Eta Carina Nebula that I just showed you. And I tagged it with color. And so here it is. I used the H alpha filter, the oxygen filter, and the blue filter to make this. And that was just my own personal choice. I just kind of wanted to see what would happen because those three images looked really different to me, and so I thought I would get different features in my color picture, and I think it turned out pretty well. This area is really turning out red, so I think that corresponds to so RGB would, I guess red would be H alpha, the green color would be the O3, and B was blue. So that's something that I've gotten really into with Skynet, and I think it's really, really fun to just mess around with the different settings in Astro Image Processor and just see what kind of different features come through. So I wanted to point that out, but I know that we're getting short on time. So any questions before we go ahead and move on to the investigatable questions discussion that I think we're going to have? Do you guys think you'll use the Astro Image Processor to make some color pictures with your filters, filtered images?
Absolutely.
Yeah, it's really fun.
So I did have some problems with getting the Astroglow or whatever, the after filter thing. I had some problems. It wouldn't download for me.
The Astro Image Processor program?
Yeah, the Astro Image Processor would not download. I'd click it and nothing happened.
Okay, were you doing it on your work computer? Because I think that's been Sue-Ann's problem is
okay.
Getting it on her work computer. Would it be possible to try it on your home computer? Let's see. I'll click it right now and see what happens.
Catherine, when you did your images, did you do them all for the same exposure time, or based on the filter, did you change your exposures?
I did all the same exposure time because that was for those were from my investigating filters activity where you're really kind of doing an experiment where you're keeping everything else the same. So I used the same exposure time for all the images. So can you see my screen where I'm clicking on, this didn't come up for you? I don't know who just asked me about that.
All it does is reload, make a color image.
Oh, okay. I think I ran into this too. There are two places where you can get a link to Astro Imaging Processor. One is actually inside the filters activity. There's a link that doesn't go anywhere. It says, oh, make a color image, and it doesn't.
It goes nowhere.
But if you look at resources up at the top, that link works.
Okay, I'll try the resources. Thank you. I was going nuts. I knew I was doing something wrong. I couldn't figure out what it was. Okay, thank you.
It took me forever, but no, now we got it.
Yeah, you weren't doing anything wrong.
Another bug.
Broken link. Yeah, that needs to be fixed. So it should go there, but it didn't. So that'll be something we'll want to post maybe, Anna, on a follow-up to this web chat. But until we get that fixed, people can get a good download of this from the resources page.
So I just downloaded the Astro Image Processor, and what came up was Stone Edge. Is that correct?
It's also called Stone Edge, yes.
Okay.
So I have a quick question for you. When you're in Skynet and you're adding an observation, you have the option of selecting the different filters, and there's some information that comes up in the box to the right. What would be the most useful information for you about the filters? Right now, it's kind of a general statement about what a Sloan filter is, that they're filters between this range, which is right for the detector. But what would be concrete for you that would say, oh, that's why I'd want to pick a red one, or that's why I'd want to pick a blue one? What kind of information?
something about what that's telling us about the object. You know, like, is that residual blankness or, you know, whatever it means.
Also, could it tell us what kinds of objects it's more likely to bring out features in, whether nebula or planetary objects? Those have two different kind of definitely two different brightnesses. So maybe one filter may be better at bringing out detail in nebula versus the moons around Jupiter.
That's good.
Okay. Because I remember Josh asking me that at one of the workshops that we did in West Virginia when he was actually there, and I thought, I'm not sure what would be the most useful. I mean, because you could say sort of the range of wavelengths that it lets through, and that's fine for perhaps the science, the research astronomers, but for you guys to be able to connect to that information, we need to have relevant information there to you, because giving a range of wavelengths still might not be relevant if you don't know what that means, what things that's associated with. Okay, good. Thank you.
Any other filter-related Okay, I'm going to turn my webcam on and talk a little bit more about investigatable questions, because we didn't get to talk about that last week, and you guys have asked a lot of them. So James, I think you're on today. Let me peek down through here. Are you on this web chat?
Yep.
I'm going to pick on you, James. Because you have asked a lot of investigatable questions, but you were one of the ones that said, I don't know how to come up with one of these questions. I'm not sure what type of question to even begin, but you've come up with a bunch of them. So I'm gonna talk about some of the ones that I have found by looking